This video examines the centripetal term that popped out of the transform between the inertial and rotating frames of reference. Following on from the last video, here we have the Navier-Stokes momentum equation in terms of the velocities in the rotating reference frame, UR, which includes the Coriolis term and the centripetal term. From basic vector calculus, a triple vector cross product can be expanded like so, giving the difference of two dot products. For the centripetal term, this becomes omega outside of omega dot x minus x outside of omega dot omega, where omega describes the rotation of the reference frame and x is some vector. Cast in terms of the rotating reference frame, x consists of a component that is along the axis of rotation, z, and a component that is perpendicular to the axis of rotation, r. It is useful to make the substitution for x with z and r. Recall that r and omega are orthogonal, so their dot product is 0. Z and omega are in the same direction, so the omega z here is cancelled by the z omega here, leaving just the radial component and omega squared. We can go one step further and express this as a gradient of a potential in R. We do so by integrating and differentiating the right-hand side in R, returning the centripetal term as equal to the negative of the divergence in radius squared by omega squared over 2. Recall that there is another term in the Navier-Stokes equation that is also a potential in R, gravity. As a potential in R, the centripetal term can now be combined with the gravity term to define a geopotential term, phi, where phi g represents the gravitational potential. Physically, this geopotential term combines the local gravity with the local centripetal accelerations by considering the radial distance to the axis of rotation. So for Earth, this term is a minimum at the poles, where you are on the axis of rotation, and a maximum at the equator, and it varies between them as a function of latitude. Now, over billions of years, Earth has shaped itself such that the surface reflects this geopotential. Earth is not perfectly round, but is actually oblate, so that for studying something like the ocean's surface already follows a geopotential, thus already accounting for the influence of centripetal acceleration. We substitute this geopotential term back into the Navier-Stokes equation to recast these momentum equations in terms of the centripetal corrected gravity.